has always wanted to extend his activities past sunset. Fire was his first artificial light, but it was difficult to transport. Then came grease lamps, gouged out of soft rock. These allowed the first artist to go deep within caves. Each new form of light marked an era. The grease lamp that must be regularly refilled, the candle that drips on one's fingers, the kerosene lamp, smelly and dangerous, until, around 1900, the arrival of magical electricity, as bright as daylight. Light has long been considered divine. If we go by our cultural references, the Greeks were the first to study it. For them, light was closely linked to vision. The mathematician Euclid had the brilliant idea to represent it by thin rectilinear threads, luminous rays. He believed that the eye sent out rays to strike objects, which allowed them to be seen. Civilizations disappear, but libraries remain. In their conquest, the Arabs recovered Greek works and translated them. They inherited ancient knowledge, deepened it, and brought further innovations to it. In the year 1000, Alhazen understood how the eye functions and confirmed, contradicting Euclid, that light comes from objects. Even more importantly, based on countless experiments, he put forth the laws of reflection and refraction. Alhazen symbolized Arabic science at its apogee in the Middle Ages, a new science based on observation, experimentation, and measurement. His books were translated into Latin and circulated throughout Europe. Copernicus, Kepler, and Galileo read them and were inspired by them. As with many other areas, it was a renaissance for science. Galileo passed from geometric optics to instrumental optics by creating a telescope that he pointed toward the sky. He discovered thousands of stars in the Milky Way, craters in the moon, Jupiter's satellites, here is Io, and sunspots. He asked himself, how fast does light travel? He wanted to measure its travel time between two hills in Tuscany using flying lanterns, but in vain. These instruments were too primitive. The experiment would have appeared pointless to René Descartes, who believed, like most scientists had since antiquity, that light spreads instantly. In 1637, he established the law of refraction, but also searched for a solution to the problems of geometric optics. He had the great insight to return to the nature of light and launch a debate that would last 3 centuries. 25 years after the death of Descartes, the Danish astronomer Ole Romer, working in Paris, studied the movement of Jupiter's satellites used as clocks by navigators. He perceived irregularities. Io, for example, rises later and later as the Earth gets farther away from Jupiter. Romer attributed this gap to the additional time taken by light to reach Earth. He estimated the time at 22 minutes for light to pass through the Earth's orbit. He could calculate the speed of light using simple division, but unfortunately, orbital dimensions were still not well understood at the time. However, the result was there. Light has speed, and this speed is not infinite. This was good news to Huygens, the Dutch mathematician and astronomer. It supported his theory that light is a wave, a vibration that travels. His theory conflicted with that of an eminent English thinker, Isaac Newton, for whom light was a stream of particles. Each of the men interpreted the phenomenon of light in his own way. Take refraction, the changing of direction of light when it passes from one transparent medium to another, from air to water, for example. For Huygens, if there is refraction, it is because the speed of the light waves decreases when they penetrates the surface of the water. Newton, on the contrary, used the rules applicable to the ballistics of projectiles. If there is refraction, it is because the speed of the particles increases. This wave-particle controversy would inspire generations of thinkers after them. In the early 19th century, Young, Malus, Fresnel, and Arago discovered the phenomena of diffraction, interference, and polarization, which proved the wavy nature of light. But Newton, who had found an explanation for the gravitation and movement of planets, had received immense glory, and many thinkers called Newtonians remained partisans of the particle theory. To define his theory, Arago proposed experimentally comparing the speed of light in water and in air. Foucault and Fizeau developed revolutionary laboratory equipment to determine the speed of light, the first using a rotating mirror and the second a serrated wheel. The key experiment was conducted in 1850. Verdict: the speed of light is slower in water. Huygens was right. The triumph was completed in 1865 when Maxwell achieved the brilliant synthesis of electricity and magnetism. Light is the sum of two waves, an electric wave and a magnetic wave. Light is an electromagnetic wave. Was the debate definitively closed? No, for in 1885, Hertz showed a new phenomenon. A metal plaque, lighted by ultraviolet light, emits electricity, while with red light, nothing happens, even when the intensity is increased. This photoelectric effect is impossible to understand if light is only a wave that carries energy. Inspired by Planck, Einstein gave the credit back to Newton's particles. He announced in 1905 that light is composed of quanta, later called photons, particles without mass whose energy depends on the frequency of the associated wave. Thus, depending on the nature of its interaction with matter, light manifests itself as either a wave or as particles. It would take some time to admit this subtle truth, this wave-particle duality, which was stated by Broglie in 1924. Light is a truly exceptional phenomenon in the history of science.
No.